So good afternoon, everyone. Today I have the great pleasure to welcome Professor Cara Schwarz. Professor Schwarz is currently a professor at the Stellenbosch University, South Africa, where she also graduated and completed her master's and her PhD on chemical engineering. She is an experimental thermodynamicist with nearly 20 years of experience in space behavior measurements. Her field of expertise is related to the impact of separation process with a particular focus on high pressure, supercritical, and advanced distillation process. Through her career, Professor Schwarz has received numerous awards, including the C1 NRF rating in 2016. To date, she has published 70 publications in international journals, and she also made 112 conference contributions. So once again, welcome, Professor Schwarz. Thank you so much for being here. And please feel free to share your screen and start your presentation.
Thank you very much for the introduction. I'm just going to share my screen and then hopefully everything will look better then. Okay. Can somebody just confirm that you can see my screen?
Yes, we can see our screen. Thank you.
Yes.
Okay. Thank you very much. Thank you very much for the introduction. As mentioned, my name is Cara Schwarz. I am a professor of chemical engineering at Stellenbosch University. And you've said a bit about me already, so I'm going to start by just saying a little bit about Stellenbosch and Stellenbosch University. So Stellenbosch is a town about 50 kilometers east of Cape Town. It was established in 1679, and it's the second oldest Western settlement in the Western Cape province of South Africa. It's got a population of today probably about 180,000 people. I guess in the 2011 census, it was 156,000 people. And it's generally well known for its wine, its tourism, and its university. As mentioned, I got my degrees here. So I've been in Stellenbosch for quite a long time. In fact, I also went to school here. So let's go back to the university. So our university is a medium-sized research-intensive university. It's publicly funded, and in 2020, we had approximately 31,500 students. We are an academic university with 10 faculties on 4 campuses, 8 of which, including the Faculty of Engineering, is on the main campus here in Stellenbosch. The university was established in 1866 as Stellenbosch Gymnasium, and after a few different names and different versions, in 1918 became known as Stellenbosch University. So in 2018, we had our centenary, hence the 100 logo. So that's a little bit about the university. As mentioned, I am from the Faculty of Engineering, from the Department of Process Engineering, and I regard myself as an experimental thermodynamicist. And this all started in 2000 when I built the phase equilibrium cell you can see here as part of my master's project. So that was the first phase equilibrium, or the first in this particular version of the phase equilibrium cells. And then we went and built a couple of different modifications of that, one of which is the setup you can see over here. And this particular setup is unique insofar as it's got 2 Rolsey samplers. What's unique to our department, that it's got these Rolsey samplers, so we can actually take samples of the coexisting phases. I'll get back to this one a little bit later. But my work, although I started in the supercritical, the high pressure and the supercritical side, my research didn't only focus on that. It also these days focuses on low pressure phase behavior measurements and how they're all linked together. So that's just a little bit of background regarding where I come from. So today my title is Phase Equilibria in Fluid Phase Systems, the Kinetics of Equilibrium. And what I actually want to do is I want to just pose a question, which I don't really have an answer to, but one can maybe put that as a point of a discussion, and that is why is the kinetics of attaining equilibrium important in phase equilibrium measurements? So if we look at my title, there's 3 different concepts here. There's phase equilibria, there's fluid phase, and then there's kinetics and equilibrium. So if we start with equilibrium, it's a state in which opposing forces or influences are balanced. It's a state of being physically balanced. it's a calm state of mind, it's a state in which a process and its reverse are occurring in equal rates. So there's no overall change. So we get the general idea that equilibrium is this balanced state where nothing is actually changing on a macroscopic scale. Fluid phase systems, for what I refer to them, are the systems in which the molecules can move freely. So in other words, your vapor and your liquid systems, and then of course also your supercritical phase behavior. So that's just a concept of where it's the basics of it. So if we go and have a look at the phase equilibrium of these systems, we generally have a balance of temperature, pressure, and composition of these coexisting phases. So coming from Stellenbosch, of course, I'm going to bring wine into it. So let's have a look at the bottle of sparkling wine. And let's reduce our wine to a water ethanol mixture because, of course, I'm an engineer, so I try to make things more simple. And we've got carbon dioxide to make it sparkling. So if we want to go and do a phase behavior study on that, the questions are, what is the equilibrium composition of the water, the ethanol, and the carbon dioxide in the liquid and the vapor phases? And how long does it take to reach equilibrium? And how do we know we are at equilibrium? And it's more these last two questions that I'm going to focus on, not so much the actual compositions. Okay. So kinetics, sorry, that's gone too fast. So kinetics is the branch of chemistry concerned with the rates of chemical reactions, or if you go and have a look in terms of physics, they also describe it as a term for dynamics, which in turn is the branch of mechanics concerned with the motion of bodies under the action of forces. So here you have keywords such as rates, motion, action. So what kinetics and equilibrium do is kinetics is how fast we get somewhere, and equilibrium is how far can we actually go to get there. So those are the two aspects that we are going to consider, or I'm going to just talk a little bit about in this presentation, because as thermodynamicists, we very often focus a lot on equilibrium. We don't really focus so much on the kinetics. So I'm going to have a look and see how far or how fast do we get there. So my presentation today basically will consist of the thermodynamics of phase behavior, measuring it, getting there, detecting it, and quantification. So that's all about phase behavior. Linked to that will then be the kinetics part. And I will ask the question on how long does it actually take to reach phase equilibria, and how do we know we are at phase equilibria? All of this ends up coming to the point, what is the role that kinetics plays in phase equilibrium measurements? So let's start by having a look at the thermodynamics of phase equilibrium. So I can probably speak for hours on end on the theory, but let's just have a look at the very basics that we need in order to understand the concepts further. So let's start again with our wine, or our sparkling wine. And we have mechanical equilibrium when the pressure is constant throughout our bottle. We will have thermal equilibrium when our vapor and our liquid phases are equal in temperature and the temperature doesn't change. And then we have what we call chemical equilibrium. And chemical equilibrium is the equality of chemical potential, as we all know as thermodynamicists. And here we know that the compositions are not necessarily are not necessarily equal, but they may be constant. So what we have is we've got compositions that don't change with time. And the criteria for chemical equilibrium is that the chemical potentials are equal. In other words, the chemical potential of your carbon dioxide in your vapor phase equals that of the chemical potential of the carbon dioxide in the liquid phase. And we can extrapolate that to the other components. We can go and develop lots of theory around this, but let's just start off with this particular system. And if we have a look at carbon dioxide, water, ethanol, carbon dioxide has a quadrupole, water has a dipole, then our ethanol also has a dipole on it, and it has a little bit of a hydrocarbon backbone. And then because we are working at pressures, typically 4 or 5 bars, your bottle will be at, we have a non-ideal vapor phase. So the dipole, the quadrupole, the hydrogen bonding, the non-ideal vapor phase, this results in a system with complex molecular interactions that are very difficult to describe. In fact, if you go and have a look at state-of-the-art thermodynamic models, they're not able to predict these intermolecular forces with sufficient accuracy that these models can behave predictively. This leaves us with the fact that we need experimental measurements. And that's where I come in as an experimental thermodynamicist. Well, that's where I see as my role. So let's have a look at what we need from these measurements. So we want to go and actually go and get our equilibrium. And when we take our bottle, we can go and apply Duham's theorem. And Duham's theorem is based on the degrees of freedom analysis. And if you go and do a degrees of freedom analysis for a bottle or for this particular system, we see that it is a closed system. And if we know exactly how much material is in there, or rather if that material is fixed, then everything else in that system is fixed. So if we have a certain quantity of water and ethanol, and we add a certain amount of carbon dioxide, and we close the bottle, then when we have a certain temperature in this particular fixed volume, our pressure outlet is fixed. So in a particular closed system, we only need these two variables. And that's important when we go further looking at our methodology for our measurements. So let's look at how we do these measurements. So before we look at how one does the actual measurements, let's consider the phase boundaries and phase equilibria. So if we have a triangle or a ternary system, and here I've just taken a system from one of my previous PhD students, you'll see that we have three regions. We have a liquid region, we have a vapor region, and then we have the two-phase region in between it. This should be reasonably well known. So between our two-phase and our one-phase region, we have a phase boundary. And one type of measurement we can actually do is to go and measure exactly where that boundary lies. So the white blocks and the thin black dotted line here was a phase boundary measurement, or that data comes from phase boundary measurements. Alternatively, we can go and measure our vapor and liquid compositions that are in equilibrium with one another. So for that, we get two data points. We get vapor phase, we get a liquid phase, and we know they are in equilibrium with one another. While these two methods give us different types of data, if they're conducted correctly, then they should lie on one another within the experimental accuracy, like we can see from this particular study. So if we go and have a look at phase boundary measurements, here the majority of them would either be bubble point or dew point measurements, where we have a known composition. We put it into some kind of setup. I'll get to that in my next slide. And then we will go and set the temperature usually, and we change the pressure until we see the phase boundary occurring. A bubble point pressure, of course, would be where the first little bubble forms. A dew point will be where the first little drop of vapor forms. But in the high pressure region, you can also have what we call a critical transition. So here you have a transition from the vapor and, or where you have the transition close to the mixture critical point, where your meniscus or your interface between your two phases disappears. And typically, such measurements are conducted in a phase equilibrium cell that looks like the one I have on my screen here. And this is the picture of, or schematic from my master's study many years ago. And we have a pressure chamber, we have a sight glass. So in my pressure chamber, I have a known mixture. And then with my light source and my optical sensor, I then can have a look and see what's going on. So I set it to a certain temperature, and then we change the pressure to observe the phase transition. This is a rather easy, not easy, but it's an easier type of measurement. Phase equilibrium measurements give you more information because you actually get the composition of the coexisting phases, not only the phase boundary. So this can be done either statically, where you have your mixtures in a particular unit, and then you take samples or you analyze the compositions, or you can actually recirculate it. And this particular, whether you put recirculation on, actually depends on various different aspects, and also information such as pressure, temperature, etc. So I promised I would get back to this phase, this setup. So this is one of our more advanced setups in our system. So we have a variable volume view cell. Looks very similar to the one I had 2 slides ago. And we have a heating bath, and we can go and see what's going on inside. That's very much the same as the static analytic setup. What makes a difference, though, is that we've got these 2 Rolsey samplers. So these samplers can move up and down within the phase equilibrium cell, and we can take samples with these samples and transfer them to an online gas chromatograph. So that's essentially how this particular setup works. Just to give you a little bit more information, if you do a cross-sectional cut through the setup, this is typically what it looks like. You've got your 2 samplers, which is that R, the 2 R samplers. You've got a GC, and you will then take the 2 samples and transfer those samples onto the GC. So this is typically what we do at high pressures, and when we have expensive components that we need to analyze, or rare components. Stellenbosch University to measure VLE and VLLE. It is a commercial setup. It's a pilot test VLE 100. And here we have redrawn the setup, my student sundry. And what we have here is we have put our feed into our burette, and it goes into the mixing chamber, where it's then partially evaporated, and the mixture moves up the Cottrell tube. Your liquid mixture goes back, and your vapor mixture exits the top and is condensed and returned to your mixing chamber. And then you can take condensed vapor and liquid samples from that. So here we have an example where we do have recirculation in our system. But that's not what my talk is about. My talk is about the kinetics. And how do we get to phase equilibrium? In other words, how long does it take to reach phase equilibrium? So if we go and have a look again, phase equilibrium is when our pressures are stable, our temperatures are stable, as well as our compositions. So we need equality of temperature, pressure, and chemical potential. And the question is, when does that happen? So let's take a microscopic look at what's happening. So we know that between our wall surface and our 2 bulk fluids, we've got a certain amount of heat transfer happening. So if we'd taken that bottle and we put it into the fridge to cool it down, the wall would be colder than the bulk, and we'd have a certain amount of heat transfer happening. Because our 2 phases have different heat capacity values, we then also get heat transfer between our phases and our surfaces, and then between the 2 surfaces as well. So that's the heat transfer happening, and that is to get to our equality of temperature. To get to equality of chemical potential, we need a certain amount of mass transfer to happen. So we've got a closed system, so there's no mass transfer over the system boundary, but we do have mass transfer happening between the bulk of the 2 different phases and the interphase. So that is what was happening. So there are a couple of equations on here. I'm not going to go into very much detail on them, but dF stands for the driving force. So what we see here is there is a driving force for heat transfer, which has got to do with a temperature difference, and the driving force for mass transfer has got to do with a concentration difference. So let's just keep that in mind and have a look at the equations that dominate heat and mass transfer. So we have predominantly convective heat transfer happening here, and that, as I said, is dominated by the difference in, well, the driving force is the difference in temperature. Convective mass transfer, again, is the difference in concentration. And those are the equations that are aligned here. And these driving forces, however, become smaller as equilibrium is approached. So therefore, the heat transfer becomes slower and the process slows down. We can't do very much about those different driving forces, but we do have heat and mass transfer coefficients. So these coefficients are influenced by temperature, pressure, and importantly, the composition of our systems, and also, of course, the movement of the molecules. So we all know these basics. We put that all together, we get a very complex mathematical relationship with ill-defined or undefined functionalities. In other words, trying to quantify what's happening here is going to be very difficult and probably end up being a master's or a PhD study on their own, and which, of course, would have to be redone for every new piece of equipment. So as engineers, we can't actually afford that time. So what do? We just leave our setup long enough and hope that we are, in actual fact, at equilibrium. But we can actually do something about getting there faster. So both heat transfer and mass transfer are boundary layer phenomena. So that's where the driving forces actually take place, and that's where all these underlying concepts actually take place. So what we can do is we can actually introduce some mixing, because mixing will improve both your heat and your mass transfer. So it will increase the movement of the molecules to increase those transfer coefficients, and it will also increase the area of mass transfer. So you might not have an absolutely still surface. You could possibly, by having mixing, create many other or rather complicated surface, and then we will get mixing that can help create more uniform phases. So all of this will lead us to the fact that mixing actually helps significantly, but that still doesn't solve our problem. At the end of the day, we still need sufficient time, and it can just be a little bit less time than normal this time. So if we can't actually know how long we need to get to phase equilibria, can't we just go and detect it in some way? So back to my bottle. So if I want to go and detect mechanical equilibrium, I've got equality of pressure. If I want to go and detect my thermal equilibrium, I can actually go and measure my temperature. But to the best of my knowledge, one cannot yet go and measure chemical potential. So what we do is we typically go and we can go and measure our compositions. We can make sure that our compositions are in actual fact constant. So if they are not changing, it does give us an idea of the fact that our equilibrium will be attained. But it's not always easy to go and measure these compositions. So what we sometimes do is say, if pressure and temperature is stable, the question is, can we then assume our chemical composition is stable? So let's have a look at the water ethanol system. So we all know that this system has a temperature minimum azeotrope. And if I actually go and zoom into that, the 1 degree Celsius around that particular system, we can see that even if we limit it to the lowest 3 degrees where there's data, 0.3 degrees where there's data available, if we have constant temperature, it's still not going to tell me that my compositions are constant. This means one does actually need an alternative to show that you are at equilibrium. So we do a combination of things. We allow sufficient time. That's going to be the answer very often to a lot of things. And we also have we go and test our methodology. So we take our setups, we go and prove that we are able to reproduce additional experimental data. And that is something that I, as a reviewer, am very pedantic on, to make sure that the methods are actually reproducible, and my students know that as well. So for me, they need to do that too. So methodology verification, of course, is very important. So detecting phase equilibria is not that easy. So can't we just go and quantify quantify it? Well, if we're just doing a phase boundary measurement, it's rather easy. Here our compositions don't change, so we just need equality of temperature and pressure, and we can actually go, and when they're stable, we can actually go and do these measurements. But unfortunately, it's not quite so easy when we want to do some phase equilibrium measurements. If we go back to Durham's theorem, and that's why I introduced it earlier on, if we go and take a small amount of our vapor phase and our liquid phase out of our system, the known quantities of our masses actually change, or the quantities of our masses actually change. And therefore, we are in fact disturbing equilibrium. So if we want to go and do these measurements, we need to go and take these samples, and we need to be very careful when we take these samples. These samples need to be representative, and the samples then need to be representatively analyzed. In other words, the samples we take, we need to get onto a GC or any other device that we're going to analyze them. Then, preferably, the samples should not cause a disturbance. In other words, you shouldn't be disturbing the equilibrium. And then also the samples should be, all phases must be sampled simultaneously. So I said preferably you should not disturb the equilibrium. Well, what one can do is you can take a little sample, and if you sample them simultaneously and during your sampling you don't disturb equilibrium, then it's fine. You can use those samples, you just won't be able to repeat your measurements. So if I look at my VLE and VLOE setup, what we see here is that we can take these liquid samples. So we have a liquid phase and a vapor phase sampling point. And these sampling points, what one can do is if you actuate them simultaneously, sufficiently small samples are taken, then these samples are in equilibrium with one another. But unfortunately, we can't go and repeat the samples. So for low pressure, this is not such a big problem. But when we get to our high pressure unit, it's significantly more difficult. Because here, if we take a very small sample, the density might change, because our density changes significantly with a small change in pressure or temperature. So, and if our density changes, then we will end up having a change in solubility. Also, when we close the mixture critical point, we have a significant amount of issues. So our student, Frederick Fourie, spent a lot of time on the sampling. And in fact, I think it took us probably about a good part of a year to actually sort this all out, to figure out how to representatively take these samples and get them onto the GC. In the end, these samples need to be extremely small, because otherwise we end up getting significant disturbances. And if you're interested in that, I can actually send you references on the papers on that, where we actually describe this in the open literature. So getting back to how we do our sampling. So we can go and do all of this, but if you have enough money and you have the ability and the correct system, I would also recommend you consider spectroscopic or gravitational methods. So if I know Professor Breuer in Germany is doing a significant amount of work where he's looking at how one can quantify the compositions at high pressures using Raman spectroscopy. But it's also quite complicated. Some of those setups are quite expensive, and it's also limited to certain systems. Your carbon dioxide, ethanol, water system will probably be nearly impossible to do those kind of analyses with, because your infrared spectra lie on top of each other. So as I come to the end of my talk here, I want to ask the question, what role does kinetics actually play in this? So when we start off with our ethanol and our water, together with our carbon dioxide, we want to be able to get to our equilibrium point. So kinetics is a transient process, and it's the process that actually, or that what dominates, that gets us from our initial condition to our equilibrium condition. Temperature and pressure and concentration differences are the driving forces, yet the proportionality constants are influenced by your temperature, your state, in other words, your composition, then your state, which is your temperature and your pressure, and then also the degree of mixing. So if I take my carbon dioxide, water, ethanol, and I shake it a little bit, I will get to my equilibrium point a lot faster. Faster kinetics also leads to faster equilibrium, but we also need to consider that we may need to disturb the equilibrium if we want to actually determine if we are at equilibrium. At the end of the day, ladies and gentlemen, phase equilibria, or the kinetics of phase equilibria at the moment, is still more an art than science. And what we need to do at the end of the day is we just need to put in sufficient time in order for us to be able to ensure that we're at equilibrium. Thank you very much, ladies and gentlemen. I've now come to the end of what I've prepared for you. I hope this talk will give a number of questions. Just before we go to that, a little bit of typical South African information. We have what we call rotational electricity cuts for approximately 2 to 4 hours. And this is what we call load shedding. So here in Stellenbosch, we're going to be load shedding at 6 o'clock. I'm in the office. I do have a generator. So if I do go offline for a few minutes close to 6 o'clock, I will be back in a minute or two later. So, any questions?
Thank you so much, Professor Schwarz, for your lovely presentation. It's a pleasure to have you here with us. And we are now open for questions. If you want to ask one, please feel free to enable your microphone or write it down in the chat so we can read it. Our YouTube viewers can also ask questions, of course. So who wants to be the first one?
Can I?
Sure, go ahead, Professor.
Hi, Cara. Let I ask you something. Your example was you have the two phase already settled. Yep. So we are worried about the concentration evolution, the time or the temperature evolution, so on. But suppose that you have the second phase already. So it's about to get the second phase. So so you know the concentration, temperature, and so on from one phase. That's a big phase, and it's going to appear the second phase. So we have the nucleation. So it's much more, it means complicated situation that maybe the kinetic problem play very strong role in this situation. So it's kind of math that you have the one phase and create a second phase. So the nucleation, for example, for solid phase is crucial.
Yeah.
What you have comment about that?
So on the solid phase, I can't really say anything or say very much. I've got very little experience on the solid phase. What I can say is if I compare our static analytic methods where we have a single phase and then we let it get to thermal equilibrium at a pressure where we are in a single phase, and then we change the pressure incrementally but slowly, those measurements are significantly faster than what it is to measure phase equilibrium. So if I actually just, let me just go back to my presentation here. Actually quite near the start. You will, it's quite far up the front. You will actually see that those, just want to get to the triangle diagram, sorry.
Okay.
You'll actually see that that is why we have so few ternary or VLE measurement data points compared to if you go and get your phase boundary measurements. Nearly there. So if I have a look here, it takes me, I can do on one composition here, I can do about 5 to 6 different temperatures and then the phase transition pressure for that in a day. Whereas an equilibrium composition on these here takes me about 3 to 4 days to just do a single equilibrium composition. So that does play a significant role. It's a lot easier to get to these kinetic effects, to get that sorted in a single phase because you don't have to go over the phase boundary.
Okay.
I hope that answered the question.
Yes, I understood what you're talking about. I was worried about the solid phase, so that's okay.
Yeah,
because you know that phase will have memory effect, or if you have a like a pharmaceutical substance that's a solid phase, it takes you some maybe, I don't know, but long time to, or you have oversaturated a lot to get this solid, and you never know what the polymorphism you are getting if you not analyze like with X-ray or something like that. So I was worried about this.
Yeah, so I've actually stayed away from the solid phase, partly because our sponsors have generally been the petrochemical industry. But my limited knowledge is that it takes orders of magnitude longer. So it will take, I would guess, probably days for it to get to equilibrium, if at all. And again, you never know if you actually are there. You've got different types of phases. So yes, that does take quite a lot longer.
Well, one solid phase that is important for petroleum industry, for oil company, are hydrate formation, and other is wax precipitation. So you are not measuring this kind of stuff.
So I'm not measuring that particular stuff. So I've got a PhD student. She's working at the CSIR, so that's like a government research facility, and at her facility she actually does measurements for the solid CO2 phase behavior of waxes. So she's done work like that. If you go and dig deep into my PhD, I had a look at the crystallinity of alkanes and waxes and all that kind of stuff, but that was more on how it comes into the liquid phases. So we haven't actually done very much work there, but that is an important point in terms of the petrochemical industry. And also with the waxes, you very often get melting point depressions and that kind of stuff that we've had a look at. We're looking at possibly doing 1 or 2 projects on hydrates in the future, but that will probably is still on the way.
Okay. Can I ask something about your cell, high pressure cell?
Go for it.
I wonder, your cell, what the pressure that you can go, how far you can go, and what kind of O-ring you're using for carbon dioxide, and in your sample, what the dead size of your line compared to your cell?
Okay, so we've got 1, 2, 3, I think 5 setups here for different phase equilibrium cells. 5 setups. 3 of them go to 150 degrees and 300 bars. One other one goes to 120 degrees and 300 bar. And then we've got one setup where we can take up to 300 degrees Celsius, but only 150 bars. So that gives you our temperature pressure ranges. They all look based on a very similar setup to this setup. And we end up using Teflon as O-rings because the carbon dioxide goes through the Viton O-rings. And at some place, in some positions, and for our our high temperature phase equilibrium cell, we actually have used aluminium for some of our seals on there. So, and we also used glass-filled PTFE. And you can see here on the schematic, the volume. So our volumes inside here, they vary a little bit, but we typically have between 20 and 80 milliliters. So it's about a double, so 20 and 40, and then about 30 to 80 milliliters. So we typically add between, say, 10, depending on the materials we're adding, the amount of high pressure, gas and all that we add. It will be between, say, 10 grams and maybe up to about 45 grams, depending on the actual system that we're looking at and which one of those cells we're actually using.
Okay, thank you.
More questions?
I have a question, please.
Please go ahead.
Yeah. Hello.
Papa, can you open your camera?
Yeah. Still having. Okay, right now. I have a question about the pressure control when you are using a sampling system.
Yeah.
Yeah, because generally you have some disturb about the pressure control, and how you can minor it.
So it actually was a process, probably about over a year of actually trying to take those samples. So the samples are, first of all, very small. I don't want to commit myself to exactly the size of those samples. If you go and have a look, Frederick Fourie, if I just go to the setup, you'll see the FCVN Fourie. He wrote, I think we've got 5 or 6 publications. 2 of them on chemical engineering technology, and those 2 publications actually describe how the sampling happens. So we take extremely small samples, first of all, and then because we have a variable volume view cell, so our volume, we have the back pressure. So the back pressure will then, in fact, if the samples become larger, the back pressure actually does influence it. And what we noticed was in our phase equilibrium cells, when we took the samples, even after approximately, the samples were so small relative to the total volume that even after about 100 samples, we still didn't see a pressure difference. But there were some other effects that we sometimes saw, especially if we took the samples too quickly, or if we took the samples, if we did mixing and we didn't allow it to equilibrate long enough, then we also sometimes saw issues. But those samples were very small samples.
Okay, thank you. Another question, please. A little question. When you are measuring phase equilibrium data, generally at fixed temperature and composition, we measure the pressure transition. Okay. There is some people from literature saying that it will be different if you reduce the pressure to gain the phase equilibrium, or if you rise the pressure. But you have some phenomenological aspect of mass transfer system. You have already discussed it. What's your opinion about this?
So if I just go back to my static static synthetic methods, it doesn't actually play a role in the VLE methods, but in these methods, it actually does, or not play a role, but my experience is if you, first of all, you've got to do this slow enough. So you can't let your pressure go down too quickly. So you've got to do it slow enough, but you actually also have to, or my experience with my systems is you've got to do it from the top, from a high pressure to a low pressure. Maybe that was because by and large, my systems I've worked with are very asymmetrical. So sometimes we need an overpressure of approximately 10 to 15 bars to actually get your phases to mix together in a reasonable time. So of course, if you leave it for an infinite amount of time, they will equilibrate at the end of the day or the end of that particular time. But my experience is that if you do it from a low pressure to a high pressure, or if you go from 2 phases to 1 phase, you will sometimes overestimate the pressure at constant temperature. Whereas if you're going from 1 phase to 2 phase, you probably get a pressure that is reliable as long as your pressure drops are sufficiently small. So you take a small pressure drop, you let it equilibrate, and then you have a look and see if you've got that phase behave transition, and then you proceed from there downwards. And we've actually shown that those are correct because the measurements we get from those measurements are in agreement with our VLE measurements.
Okay, thank you very much.
Anyone else would like to ask a question?
May I, please?
Please go ahead.
Hello, Professor Cara. My name is Khalil. Sorry, I don't have camera at the moment. You talked about disturbancy and avoiding disturbancy. I'm just wondering if there is any criteria of defining if we have disturbed our sample or not. I'm just wondering about that.
So of course, there's no really hard criteria if you've got a disturbance or not. The one thing we found that's quite important, which a lot of people actually don't do, and that is the presence of that camera. So when you go and have a look at some of the older literature where people have got these phase equilibrium cells, they don't have a look and see what's going inside. And we found that we needed that visually to see what's going on inside, because sometimes you have disturbances which you can't detect from your temperature and your pressure, but you can actually see them slightly. And to give you an idea, that camera, that's quite a large computer screen or medium-sized TV screen that we have there. And what the diameter that you can actually see there is, I think it's about 30 millimeters, the diameter. So that's the resolution to which we actually can see what's going on inside there. And we very often saw little disturbances there, which we couldn't actually quantify in terms of our temperatures and our pressures. So it is quite important to have a look at that camera or to see what's going on inside, but there's no real way that you can, or one cannot always quantify the disturbances without disturbing the system.
Thank you. Thank you for the explanation.
It's a pleasure.
Any more questions? Okay, then. So I think we can maybe wrap it up now. If anyone wants to ask a question.
Okay, Simon.
Okay, let's wrap it up then. Once again, thank you so much, Professor Schwarz, for agreeing to speak in this seminar series. It's a pleasure to have you here.